Tracking a spacecraft's orientation in a zero-gravity vacuum presents an immediate mechanical challenge. You need to map its internal rotations against a fixed Earth-centered frame without any physical reference points. Drop that specific context and look at a different problem, calculating hundreds of intersecting current flows across a multi-loop electrical schematic. Or consider an industrial robotic arm that must determine the exact joint angles required to touch one precise coordinate in three-dimensional space. These appear to be distinct engineering problems, but when you strip away the hardware and the specific physical environment, they are all governed by the exact same algebraic skeleton, the linear equation AX equals B. In this system, vector B represents the known inputs, like raw sensor feeds, voltage sources, or target coordinates. Vector X holds the unknown system states we need to solve for. Matrix A represents the structural constraints of the specific system, the physical geometry of the aircraft, the impedance of the electrical grid, or the mechanical limits of the robot's joints. The computational objective across these fields is identical. To isolate X, we must mathematically invert matrix A. This process of matrix inversion is what allows us to solve for the state of a system based on its physical properties. To do it accurately, we have to look at the internal structure of the matrix itself. This is a generic 3x3 matrix, A, which we will use to represent our physical constraints. The first step toward inversion is calculating what is known as the matrix of cofactors. To find the cofactor for a single element, such as A11 in the top left, we conceptually delete its intersecting row and column. This leaves a smaller 2x2 submatrix. The determinant of this remaining 2x2 grid provides a minor value for that specific position. We then multiply that minor by the alternating sign rule, -1 to the power of I plus j, where I and j are the row and column indices. This result is the cofactor. This extraction process is repeated for every element in the grid until the full cofactor matrix is compiled. Finally, we take the transpose of this matrix, physically flipping it across its main diagonal. This resulting grid is the adjoint of A. The adjoint is not an arbitrary computational artifact. It is the specific geometric reorganization required to define the inverse of a matrix algebraically. This identity shows the direct structural link between our original matrix and its newly formed adjoint. Multiplying these two matrices together results in the identity matrix, scaled exactly by the determinant of A. To isolate the inverse matrix term, we divide both sides of this equation by the determinant. This yields the operational formula for matrix inversion. A inverse equals 1 over the determinant of A multiplied by the adjoint. Because inversion requires dividing by the determinant, this formula sets the mathematical boundaries for how we simulate physical systems. This division introduces a specific constraint. The determinant cannot be 0. As shown in this flowchart, if the determinant is non-zero, the matrix is non-singular. The system is consistent and yields a unique solution for our unknowns. If the determinant is exactly 0, the matrix is singular. In this state, standard division is impossible. To determine why a singular system failed, the software evaluates the product of the adjoint and vector B. If this product is non-zero, the physical equations contradict each other, meaning the system has no solution. If the product is exactly 0, the equations are dependent, resulting in infinitely many overlapping solutions. Calculating the determinant acts as the initial diagnostic check. It identifies if a physical model is singular before the software attempts to execute the inversion. This rapidly banking aircraft must continuously map its internal sensors to a fixed Earth-centered coordinate grid during its flight. In aerospace dynamics, matrix A is the direction cosine matrix, which contains the rotational constraints of the vehicle. The raw data from onboard inertial measurement units provides the known inputs for vector B. The flight computer uses the adjoint inversion process to back-calculate the exact spatial acceleration of the aircraft from these sensor feeds. This continuous inversion is necessary to maintain accurate spatial orientation and atmospheric navigation during flight. Over in electrical engineering, this exact same mathematical logic is used to balance voltages across complex power grids. Kirchhoff's laws allow us to translate passive circuit elements into the systemic constraints of matrix A. Active power sources fill vector B as known inputs, while the unknown loop currents populate vector X. Inverting the impedance matrix provides the network's transfer characteristics, allowing engineers to simulate how the grid responds to different loads. The algebraic derivation of the adjoint provides the method for determining these currents across the infrastructure. In the field of inverse kinematics, a robotic arm must move its joints to reach a specific point in space. The Jacobian matrix acts as the constraint grid, representing the physical joint limits and rotational axes of the robot. The target 3D coordinate is the specific input for vector B. To resolve the joint angles required for movement, graphics engines must invert the Jacobian matrix thousands of times per second. The mechanics of cofactors and adjoints provide the algebraic basis for resolving these kinematics, ensuring the robotic arm reaches its coordinate with mathematical precision. In modern practice, engineers do not perform these multi-step matrix inversions by hand. High-performance tools like Python's SymPy library automate this process. Here, we define a 3x3 symbolic matrix. Symbolic solvers allow us to manipulate variables like k or b1 directly, rather than relying on static numbers. The software arrives at the solution by following the same rules of cofactors and adjoint matrices we used in our manual derivation. The code executes these operations by applying the same rules of cofactors and determinants we used in our derivation, ensuring the output maintains its symbolic accuracy. Whether routing power, navigating orbit, or animating a robotic joint, tracing the path from cofactor to adjoint reveals how these disparate systems are solved. Understanding this structure allows an engineer to interpret why a simulation succeeds or why it fails at the singularity threshold.